Hi, everyone. So I'm super excited to be here to talk about supercharging Iceberg with DataFusion Comet. A bit introduction on my side. So I'm currently a software engineer at OpenAI. I joined OpenAI for about 2 months back. Before that, I was a software engineer at Apple. I spent about 2 years working on DataFusion Comet. I'm also a Spark commuter and PMC, and I'm also a commuter to DataFusion and Arrow. So for this talk, it's generally it's organized in 3 parts. The first, we're going to talk about some of the background, what we're going to do. We wanted to start a project, and what's the motivation for it. And then in the second part, we're going to talk about what is Comet. We can do some small technical deep dive on that. The last part of the talk will be talking about the integration between Comet and Iceberg. So the main motivation for the project is pretty simple. We wanted to improve Spark performance and efficiency. Spark has been used by many different companies in a really large scale. So many people, those companies spend like tons of money running Spark. So if we can improve Spark efficiency by say 10 to 20%, that means huge gain in terms of cost, infrastructure cost. At the same time, if you can improve Spark performance, those Spark users, they will get the answers from Spark jobs much quicker, and it will become more interactive for those people, and the user experience will become better. Another question is why don't we do incremental improvements on top of existing Spark, but instead of inventing something like brand new in this case? So there's several reasons for that. The first reason is that the existing JVM execution engine is kind of hitting its performance cliff. So it's really hard to say improve that by 2x, 3x in future. So on the other hand, a native language like Rust or C++ provides much more explicit control on memory management and performance. You can also apply different hardware acceleration such as Sandy on top of this mechanism. And also, Spark currently uses an execution approach called whole stage code gen, which is kind of different. And in the new native engine, we want to adopt a new method, which is called Vectorized Execution engine, that is easier to implement and easier to maintain. We'll talk about that a little bit later. Also, I think most importantly, some of the related work, such as Photon from Databricks, Velox from Meta, also Rapids from NVIDIA, they all proved that this approach is very promising. Like Photon and Velox, they have shown really promising benchmark numbers. So that also inspires us to follow the same approach. So in terms of SQL query execution, there are 2 mainstream approaches. So the one is called code generation, which is currently used by Spark. So what this does is basically it dynamically generates code during query compilation, right? And so for instance, in Spark, and it look at basically it generates a bunch of Java code dynamically, and those will be the actual code getting executed at the runtime. And in Spark, when Spark is doing code generation, it fuses those operators together into a really tight loop. On the other hand, there's vectorized execution, which pretty much follows the classic volcano iterator model. So each operator behaves like an iterator. It keeps pulling inputs from a downstream operator, process the input, and then return the output to the upstream operator. So, but the meaning of vectorized in this case means that the operator at one time we process one batch of rows instead of just a single row. So let's take a look at code generation. So here we have an example on the right-hand side. So this is a really simple like subquery plan. It only has 3 operators: scan, project, and the filter. So you can see in this case, basically the whole logic of this plan is compiled into similar to like the following the code on the on the bottom right. So like I said before, all the operators, they are collapsed into a tight loop. So this loop does everything like scan, project, and the filter basically. So you can see that in this case, basically one benefit of this approach is that it's really cache friendly, because everything is in a tight loop. You can pretty much say you can pretty much save the state in your register and be able to access them really quickly. And also because the code is dynamically generated, it can take advantage of type-specific information to do different sort of optimizations. And currently, Spark uses CodeGen at job stage level. So so basically between pipeline breakers. So you can see here that this is on the left-hand side. This is what you usually see from Spark Web UI. That tells you this is a whole stage CodeGen block that it contains 3 different operators. So although CodeGen has several benefits, it also has some limitations. First of all, it has certain constraints. So say if your operator becomes really complex, and the code that Spark generates tend to be really large, and sometimes it will exceed certain threshold, and that and then Spark will just give up, say I cannot actually generate that code. It will basically fall back to a different approach, to a much slower approach, which is non-CodeGen approach. Which is basically it is still like the Volcano model, but it's instead of processing one batch at a time, it's one load at a time. So it's much slower. And secondly, because the code is generated dynamically, it is not visible. It's not like you can open up an IDE, you can reason about the logic. So because it makes it really hard to debug and analyze. So you have to do different things to find out what is the actual code, what is the code that's actually executed, and then debug and look at the code. The variable names are also really not readable. So. And also, lastly, the generic code is hard to tune, because because this is also follow the second point, which is like you first have to understand the code and then be able to tune it. And also because the generic code in Spark is Java code, it runs on top of JVM, and then you sometimes have to have extensive knowledge about JVM internals in order to tune the performance. So on the other hand, Vectorized Execution model is simpler to understand. The same example as the previous on the right-hand side. So we have 3 operators, but in this case, you can see that this is basically you have this filter operator that it just takes the input from the previous operator, which is the scan, which is the project, and then we'll apply the predicate on all the rows in the batch, and then return the result to the upstream operator. So the advantage of this approach is that it's easy to implement and maintain, because it's much more modular than the CodeGen approach. Each operator behaves as a separate module, more kind of isolated. And it also has this nice property of batch level adaptability. What that means is that you can examine one batch at a time and do certain optimizations accordingly. For instance, if you know that the current batch does not contain any null value, then you can basically apply certain different code paths to, say, eliminate null checks on all the rows. So that will help a lot on the performance. And lastly, you can also apply hardware acceleration such as Sandy, because in this case you are processing column by column, and Sandy is a perfect fit for this scenario. So now we're talking about, since we have covered the motivation, the background, now we're going to talk about a bit on Comet itself. So what is DataFusion Comet? Basically, it's a native vectorized execution engine for Apache Spark. It is implemented in Rust, but it's also heavily built on top of other open source projects, in particular Apache DataFusion and Apache Arrow. And it is fully compatible with Spark. What that means is that if you switch your Spark job to use Comet, you should the same job should produce the same output as in Spark. So people should not see any behavior difference whether you're using Spark or you're using Comet. So this is a diagram on the architecture of Comet, as you can see on the right-hand side. So we have two, basically yellow blocks, they are the existing Spark operators, and those green blocks, they are Comet operators. So at the very bottom of the diagram, we have a native packet reader, which can read from different data sources such as Hive and Iceberg. And then, the packet reader, once they read those data from storage, they will return convert the data into Apache Arrow format. And then the data will be fed into other operators such as filter, join, and exchange in this case. So for each operator in Spark, we have a corresponding operator in Comet as well. And then the execution basically start from Spark, and then the control flow will be directed to Comet, and the Comet will trigger the execution on the native side. And also we have a fallback path. So if certain operator or certain expression is not supported in Comet, then the control flow will fall back to Spark for execution. And then the data exchange between JVM and the native is done through Arrow, and we do not do data copying between the two parts, but instead we just copy the pointer to the data itself. So one important thing we wanted to point out is that for Comet, we wanted to adopt an incremental rollout strategy. What that means is that we certainly cannot implement native implementations for all operators in Spark at once, but instead we wanted to implement them one by one, starting from like scan, and then we gradually go up of the operator tree. So that means also, say once we have good implementations of say scan or filter, then we can ship them to our users instead of having to wait for everything to be done. And also, like one of our top priorities is to provide full API compatibility, like I mentioned before. So if users, they switch to use Comet in their Spark application, they should see the same results from their jobs. And so we have put a lot of efforts to ensure that. So the end product of Comet is just a single drop-in jar where you can just put it into your Spark application, like Spark application class, and then you turn on certain flags and configurations, and then your Spark job should just be able to use Comet. So in terms of technical approach, so we heavily use Apache Arrow as our in-memory data format. We also rely on several Arrow-based libraries, in particular Arrow Ice, which offers many implementations for different kernels, like arithmetic operations, bitwise operations, Boolean operations, and string operations, so on and so forth. And then we have DataFusion. This is sort of like it's kind of similar to DuckDB. It's like a single node SQL engine, and it's also built on top of Arrow. So in DataFusion, they have it has different implementations for different operators, such as aggregation, join, sort. So in Comet, we want to leverage those operators as much as possible, because we don't want to reinvent those wheels. And then in terms of interaction between JVM and native, we use Genie. So which means that each Spark task will use Genie to basically each Spark task will use Genie to call a native execution for different operators. And then in Comet, we compile the query plan from Spark, which is the physical plan from Spark, into a native plan. And this is done through protobuf. So we convert the physical plan into a protobuf definition, and that is getting serialized into the native side. And then the native side is deserialized, and then you convert to a native plan. And that native plan later on will also be converted into a DataFusion plan. So this is so in this slide we basically this slide tells you more about how Comet interact with DataFusion. So as you can see on the right hand side of this diagram, those blue blocks, they're basically Spark physical plan, and then the orange blocks, they are like Comet plan, and then the DataFusion plan is this pink blocks on the right hand side. So for Comet itself, we try to delegate as much as possible to DataFusion. So if DataFusion has good implementations for certain operators like project and field and aggregation, then we basically just delegate the execution to DataFusion itself. But in some cases, we may want to override certain operators or certain expressions, and for those, we just implement in Comet itself. Because DataFusion has really good, it's very modular, and it has really good API for other people to override certain operator and expressions. So we leverage those to implement our own things on top of DataFusion. So basically the execution path is a hybrid model between DataFusion and Comet. And yeah, so on the Arrow DataFusion, the relationship is as follows. Like in Arrow, at the core of Arrow is a format itself, the Arrow in-memory format, and then gradually on top of that is a bunch of kernels which are defined in Arrow Ice, and then there's a SQL engine which is for single node that is called DataFusion, and then on top of that it's a distributed SQL engine which is called Palista. But we don't use Palista at the moment for Comet. And several of us, we are also contributors to DataFusion itself, because sometimes the semantics in DataFusion are quite different from that in Spark. So sometimes we have to make changes to DataFusion so that we can use DataFusion in Comet. For that, we also co-authored a paper this year about DataFusion and why it is a great query engine that people can extend to implement their own SQL engines. And this will appear in Sigma 2024. So the current status of the project, it is fully open sourced. I think we just open sourced it in this February, and we have got a lot of attractions and also external contributions to the project, which is really nice. And currently, it's open sourced under as one of sub projects for DataFusion. That's why it's called DataFusion Comet. I also talk about some of the current features that we support. Currently, we have done some improvements for Parquet on the read side. So we have some features called parallel I/O for S3. So that is used for when you have Spark jobs that wanted to read a lot of data from S3 some Spark jobs that are scan heavy. So in Spark, basically, when it reads from remote storage like S3, it will first try to basically read all the data from the remote storage and then decompress the data. In this particular case, is Parquet. So you first need to read the Parquet from remote storage and then decompress, and then try to do decoding on the Parquet data, and then fed the data back to the other operators. But in this approach, when it reads from S3, it is actually doing that in a sequential order. So if you have multiple column chunks, multiple pages in your Parquet data, then it tend to be really slow, especially if you're reading from S3. So we have done some optimizations to do parallel I/O in this case. So instead of using a single thread, we use multiple threads to download different column chunks in parallel. So that helped to improve the I/O performance a lot. Another feature we have implemented is called latent virtualization. So this is used for, I think in Spark at the moment, it basically, it tries to first legally materialize all the data that you read, and then apply predicates on the data. So say if you have 100 columns that you want to read, and then you want to apply a really selective filter on one single column that can filter out, say, 99% of the rows. So currently what Spark does is it reads all the 100 columns at once at the beginning, and then apply the filter on that single column. But you can see that in this case, it reads a lot of unnecessary data because 99% of the data are not necessary. So what latent virtualization allows you to do is that you, instead of reading all the data, you just need to first read that single column, and then you apply the predicate, and then you read the remaining 1% of data for those 100 columns. So you can see for this case, it can save a lot of I/O. It can help you to improve your scan performance a lot. And also our Parquet Radar is a hybrid implementation between JVM and the native. So we do I/O and decompression in JVM, but we do decoding in native. So the goal is we wanted to, because decoding is more CPU intensive, and we wanted to put that on the native side to take advantage of the native performance improvements. So far, we have implemented many built-in expressions in Spark, such as arithmetic expressions, conditionals, cast, Boolean, string, bitwise, and aggregate expressions. So I also put a link for our expression coverage. This is a link to a document in our GitHub repo. We have also implemented different operator support, such as some common operators such as projection, filter, union aggregation, sort, and join. So recently we had join support that includes broadcast join, sort merge join, and hash join. But there's still some limitations in the join support so far. Lastly, we have also implemented something called vectorized shuffle or columnar shuffle. So in Spark, the shuffle, the internal shuffle format is row-based. But in the vectorized shuffle, we switched to use arrow format for shuffle data. So one benefit of that is that this gives you better compression ratio, because you basically store the shuffle data in columnar format. So it's you can apply different compression scheme, such as dictionary encoding or Rollins encoding on top of data, which can tend to compress the data better, and you have smaller data size for shuffle data. We also implement something called async support for shuffle. So this is useful because I think in Spark, shuffle is both CPU heavy and IO heavy. Because for CPU heavy, because it needs to sort all the shuffle. Sometimes you need to sort the shuffle rows according to their partition ID, and IO heavy because you need to split out the disk. So we try to similar to what we have done for Parquet read, we try to also decode the CPU and I/O operations so that it can fully utilize CPU and I/O at the same time. So what's coming up in the future for Comet? We wanted to add more operators for Comet. In particular, we're working on window function support at the moment. We also wanted to add a lot of more improvements on the Parquet itself. So first of all, Parquet writer support, that is something we have planned for a long time. I think from what have been proved by Photon and Rapids, they have seen dramatic improvements when they switch to native Parquet writer implementation. So we ideally want to also achieve something similar. We also wanted to support complex type. Our Parquet reader right now only support primitive types. And when it sees complex type, Comet will just fall back to use Spark. So we want to add the complex type support, which can potentially also help Iceberg to support complex type. And we also wanted to support Iceberg and Delta. So Iceberg support is already done internally at Apple before we open source, but that approach, the approach we take internally is kind of like a POC approach. It's not fully fully embraced by the community. So we are working on a different approach in the Iceberg community for this effort. And also, lastly, we want to do a lot of more optimizations in terms of performance for different operators. And then, ideally, once this is done, we want to publish for TBCH or TBCDS benchmark. So, lastly, I'll talk about Comet and Iceberg integration. So first of all, how does this integration work? So on Iceberg side, it implements Spark's data source v2 APIs, which means for Spark, Iceberg is just a particular external data source. And in Comet itself, we have something called Spark session extensions, which we will intercept Spark physical plan, and we look at the nodes in the physical plan and decide what to do. So in the case of Iceberg, we look at the scan node of the physical plan, and we check whether the scan node is an Iceberg node. And if it is, then we will check if the Iceberg scan actually uses Comet or not. If it uses Comet, then we'll start a native plan. We'll basically try to convert all the following operators into native operators for Comet. So that is actually pretty straightforward for us to implement. But one tricky part for Iceberg integration is that Iceberg itself also needs to return columnar batch that is implemented in Comet. So for this, we have to basically change Iceberg itself. But luckily for us, because our Parquet reader is a hybrid implementation, like I mentioned before, the I/O and the decompression, they're done in JVM. Decoding is done in native, and also our Parquet reader is really similar to what that looks like in Iceberg. So it's similar to the Iceberg Parquet reader implementation in terms of API and the method signatures. So from that perspective, it makes it easier for us to change Iceberg to use Comet's Parquet reader when certain flags are turned on. So here it is how Iceberg implements Spark data source v2. So as you can see, Spark offers this interface. It's called Partition Reader Factory, which allows data source to implement partition reader that has two flavors. One is row-based, one is vectorized. So Iceberg has two Parquet reader implementations accordingly, which is one is the return internal row in Spark, and another is to return columnar batch in Spark. So for Comet, we only support the vectorized Parquet reader path. So because in Iceberg there's an API or interface that is called vectorized reader, that basically allows us to override the behavior and implement Comet specific packet reader. So our current approach is that we have a concrete implementation called Comet Vectorized Reader that implements this interface. So in particular, the read method for our Comet Vectorized Reader will we read from Parquet and will create a colonel batch that is implemented in Comet itself. So the colonel batch is an interface in Spark, but we have complementations on Comet that with our own logic. And then to enable Comet in Iceberg is actually pretty simple. We have introduced a new Spark SQL property in Iceberg. And so basically, as shown in this slide, for people to switch to use Comet Reader in Iceberg, they just need to turn on this flag or specify the Parquet Reader type to be Comet, and then Spark will just basically pass this property to Iceberg. Iceberg will just switch to use Comet's Parquet Reader, and then on Spark side, you will recognize this Iceberg scan uses Comet and will convert the physical plan into Comet plan. So in summary, DataFusion Comet is a new native execution engine for Apache Spark, and it's also a drop-in replacement for the Spark's execution engine. And we are currently working on Iceberg and Comet integration. And also, Comet is fully open source and community-driven. So we welcome external contributions. I think the project is basically still rapidly growing, and it's also in progress.
Hey everybody, I hear there might be problems with the sound. I think, Chow, your earbuds might have switched to a different device.
Yeah, we lost Chow's audio about a minute ago.
Yeah. No.
It's just a 1 minute ago, right? It's not a whole talk.
There you go. Now we can hear you.
Can you hear me?
Yep, we can hear you now.
Oh, I see. Sorry, I think someone just called me, and then and somehow my AirPods switched to my phone.
When we lost the last minute or so, Chow, I don't think we can back up one slide or just back up a minute or so.
Yeah. Let me. Do you know when from which side the sound got cut?
Yeah, I think we caught most of this. You were sort of describing the state of the project and where things are headed. So maybe just give us the final wrap up again. Make sure.
Yeah. So for summary, DataFusion Comet is a new native execution engine for Apache Spark, and it offers drop-in replacement for the existing Spark execution engine. Also, the integration between Iceberg and Comet is in progress. And I think there's a community PR that is being reviewed. Lastly, and most importantly, DataFusion is a fully open source and community-driven project. So external contributions are more than welcome. So we wanted to basically to collaborate with anyone who wants to achieve the same goal, which is to make Spark faster and more efficient. We have this GitHub repo, so feel free to visit it and add a star. We have a Slack channel. I think the Slack channel is shared with DataFusion, so feel free to join and add your comment or discussions in the Slack channel. Lastly, we have this bi-weekly community sync. I think just get started like 2 weeks ago. I think the last session is actually today, 9 a.m. So also feel free to participate in the community sync, asking questions and participate in discussions. That's all. Thank you so much.
Thank you so much, Xiao. That was fantastic. I have a number of great questions in the chat. We only have a few minutes, so I may not get to all the questions. If I don't, then please feel free to follow up with Xiao in Slack or offline.
Sure.
The first one is just there are a number of questions about performance. Can you give us any indication of like how in your benchmarks or whatever you have internally it's performed against say existing native implementations like a Photon or a Velox, in particular against Iceberg tables? What kind of gains have you seen?
Yeah, so we haven't done extensive comparison between Comet and Velox or Photon yet. So what we have done is basically try to run Comet on TBCH or TBCDS. So I think we're getting close to TBCH. For TBCDS, there's still some coverage, some queries that are not covered yet because it's much more comprehensive. So for TBCH, we have some numbers, but they're not final yet. And we are seeing some regressions in certain queries. But for some queries, they're pretty good. Like for Q1, I think we saw 6 times improvements. Overall, for TBCH, our current number is about 70%, 72%, which means that if Spark takes 100 minutes, then Comet will take 72 minutes to finish all the TBCH queries. But that number is pretty. It's still very early. We're still trying to figure out, there's some queries that still have regressions. We're trying to figure out why they have regressions and trying to fix those issues. So we plan to publish our official number after we fix those issues.
All right, well, we anticipate that, and everybody jump in and help. Let's open source. Yeah. Another question that came in here was about memory pressure. How does the memory space shared between the JVM and the native code? Any concerns there about basically?
Yeah, that's a good question. So for memory management, we wanted to use Spark's memory manager as a unified memory manager. So basically, on the native side, when it needs more memory, it basically asks Spark's memory manager to whether you have more memory that I can use, and basically, so that means like, basically the memory manager from Spark side will manage both the native memory and JVM memory, right? And also because we are doing that, we're relying on Spark's off-heap memory mode as default. So if you are using on-heap mode in Spark, that means that the memory manager also only manages on-heap memory, which means it will not cover the native memory part. So I think we made some changes on Spark side to make this to make the memory manager work better for our use case. So ideally, yes. So for users, from user perspective, you just need to specify what is the total amount of memory for Spark executor, and then Comet will decide and basically just use the Spark's memory manager, and that is the memory allocated for both the JVM and the native, and it will be seamlessly managed as a whole.
Excellent. Trying to sneak a couple more in here. Is the parallel I/O that you mentioned for S3, is that a replacement of the S3A file system, or is it based on S3A?
It is based on S3A. It is actually pretty similar to another improvements on Parquet side, which is called Vector I/O. I think the feature just got merged into Parquet itself. So our implementation is pretty similar. It's basically, when we have our own Parquet Reader implementation actually on the Comet side. That Parquet Reader is similar to the Parquet Reader on the Parquet side, but we have done some customizations, like the parallel I/O stuff. But ideally, in future, we do plan to switch to Swift I/O from Parquet, so that will be so in that case we can potentially just leverage the open source Parquet implementation instead of having to use our own.
All right, and that brings us to the end. There's some more good questions here I didn't get to related to Iceberg integration for field IDs and encryption and how that all interplays, but we'll have to take those offline. Thank you very much, Chao Sun. We appreciate it.